Okay, so now we're going to change gears a bit. We're going to talk about the multilayer perceptron, which is basically a neural network with a specific architecture. So I'm going to talk a bit about the perceptron, the original idea of the perceptron, and the ability of one neuron to do linear discrimination. And then we're going to talk about multilayer perceptron and how adding more layers can help us do nonlinear discrimination. So for this, we're going to look at the backpropagation algorithm and how we can learn multilayer perceptron, and also how we can use regularization when training multilayer perceptron. So the original idea was inspired on the biological neuron. So a neuron is a complex cell with many ramifications. It has these dendrites which are basically the input. They can be stimulated by stimulus from other sources, and they cause a slight depolarization on the membrane of the neuron. If that depolarization reaches a certain threshold here on the axon hillock, then it propagates quickly through the axon, and it will result in the release of neurotransmitters at the end of the axon. So the idea here is that we have something that sums all the different inputs, and when it reaches a certain threshold, it outputs a value. So it has those two components, a linear component by adding all the different inputs, and a non-linear response which, after some threshold, it outputs the value. So this basically, if the stimulus is too small, does not surpass the threshold, then the neuron doesn't do anything. But if it goes higher than the threshold, then the membrane depolarizes, and depolarizes all across the axon, and so this is the neural impulse. And this was modeled as the perceptron. The idea is that we have here this transfer function that is a weighted sum of all the inputs. So each input has a weight. We multiply each input by the weight, we sum everything, and we have this net input. So this simulates the dendrites that receive all those inputs, add them up, and give a net input to the axon hillock. And now we have this threshold for the activation function. If the weighted sum of the inputs is lower than the threshold, nothing happens. If it's higher, then the output goes to 1. So this was the original perceptron. It has this part of the weighted sum here, and then we have a bias value that just tells us allows us to adjust the size of this net input in order to make this above 0 or not. And if this is the result is greater than 0, it will fire. If the output is 1. If it's lower or equal to 0, the output is 0. So basically, this bias value here can determine the threshold for the activation. We also can include this in the vector of inputs as we did before. So one way of representing this is adding a 1 here, and the W0 would be here. So we just multiply 1 by W0 and add it to the net input. So the training for the original perceptron was simply to change the weight of the neuron. Each time there was a difference between the predicted value and the actual value that we wanted to output. So we wanted to use this as a binary classifier, so output 1 for class 1, 0 for class 0. If there is a difference, if it's outputting 1 when the class is 0, we need to decrease the weight of our input so that we lower everything a bit and it doesn't fire as much. If it's working the other way around, then we need to increase the weight of our input. So the learning rule is basically some small fraction, this value here, the learning rate, multiplied by the difference between the actual class and the prediction, the output of the neuron, and then multiplied by the input value. So if the input value is negative and we are giving a 1 when it should be 0, then we need to decrease the input. If it's the other way around, we're outputting a 0 when it should be 1. We're outputting a 1 when it should be 0. We should increase the input, and it depends on the sign of the input value and the error that we are committing. So basically, this is the learning rate for the original perceptron. We are not going to focus too much on this because we are not going to use this one. This is mostly for historical reasons. But the idea is that we are adjusting the weights to compensate the errors in the output. If we are outputting too high, we adjust the weight so that the weight multiplied by the input becomes lower, and vice versa. But one problem with this function is that we cannot compute the derivative. It's discontinuous, and we cannot use those kinds of gradient descent methods that we saw for solving the problems previously. So, in order to be able to do that, to use the gradient descent method, we can change the threshold function to something that is continuous. For example, using the logistic function. Now, we receive as input this net input here, so this sum of the weight multiplied by the input. But then we put that in the logistic function, and we get this smooth curve here, which is continuous, and continuously the derivative is continuous too. So we can use those gradient descent methods. Strictly speaking, this is no longer the perceptron. The original perceptron had this threshold function here, and did not have a logistic function for the response. However, the name stuck, and when we talk about multilayer perceptron, we are usually talking about neurons with these continuous response functions and not the original perceptron. Okay? But we are not going to worry too much about the nomenclature. The idea is that we have this weighted sum of the inputs, then we have this nonlinear response function, and we are using this to simulate a neuron. And now we're going to see how we can put them all together and train them to do classification. So let's see how one neuron can work. One neuron using that logistic function. One neuron can take in a linear combination of inputs and then output 0 or 1, or a nonlinear function of that. So this linear combination of inputs that it can receive allows it to do linear separation of our data. So basically, one neuron is a linear classifier. Actually, one neuron with a logistic function is basically the same as logistic regression, because this ends up being the same formula. The way we train it is different, but it's the same model. We are just training it in a different way. So one neuron with that kind of response function works the same as logistic regression, just trained differently. And we can use it to classify linearly separable sets. So this is a classical example. This is the R function. False and false is false, and true with anything else is true. So these are the red dots representing the true values, and the blue one represents the false, and the 0 is false and 1 is true. So this is basically just a way of representing the OR function as a classification here. And we want to train our neuron by minimizing the quadratic error on the classification. So this S will be the output of our neuron, T is the actual target class, the true class of our examples, and we want to make it so that for all our examples, we have the minimum value for the quadratic, the square of the difference between what the class of each example should have been and what our neuron is outputting. So we want to train our neuron to output 1 when the class is 1 and 0 when the class is 0. This is similar to what we're doing with logistic regression, where we are fitting that probability function that should be 1 for class 1 and 0 for class 0. So, like the perceptron, we are going to present one example at a time, and we're going to adjust the weight. So this would be the error for each example, 1/2 the square of the difference between the output and the class of the example. And now we need to change the weight of our neuron in order to go down the gradient of that error function. So remember that we want to descend the gradient of the error function. So to do that, to descend the gradient of the error function, we need to take a step in the direction of minus the derivative of the error as a function of the weights we want to adjust. But the problem is that the error is at the end after the neuron fires and the weights are at the beginning. So we have to use the chain rule to compute the derivative over all those steps. And basically, it's this one here. So we need to compute the derivative of the error as a function of the output of the neuron, then the derivative of the output of the neuron as a function of the weighted sum of all the inputs, that net input, and then the derivative of the net input as a function of the weight that we want. So with respect to the weight that we want. And this is basically the formula for each step. So we usually measure the error with this 1/2 here, precisely because it will cancel the 2 that comes from deriving the square. So this would be the first part, minus t minus fj, for that derivative. This minus will then cancel with that minus, and we are left with only this one. The second part here is the derivative of the logistic function, which is basically the output of the neuron times 1 minus the output of the neuron. And then we need the derivative of our weight, of the input for the logistic function, the net input, with respect to our weight. But since this is a linear combination where we multiply each weight by the input, the derivative is simply the input. Okay? So these are the different terms. So basically, we have this update rule. Every time we present an example, we want to give a small step in the direction where the gradient is falling, so minus the derivative with respect to that weight that we're going to update. This small step is typically something between 0.1 or 0.5. We don't want to give steps too large, or else it will not converge. And so, when we do this computation, we have this update rule. We multiply that learning rate by the difference between the output and the firing of the neuron, then multiplied by the output, difference between the class and the output of the neuron, then the output of the neuron, 1 minus the output of the neuron, and the input value that goes through that weight. So each weight is updated in this way. So the intuitive explanation here is that we have this target class that we want. We are comparing that with the result, with the output of the neuron, and we need to propagate the error all the way to the weight that we are multiplying by the input here. So that's why we have to go back through all those derivatives. We need to compute this difference, the gradient in the quadratic error, then go through the function towards the weight. Okay, so that's the intuitive explanation for that chain rule for the derivative. And this is what we're going to do. We're going to do stochastic gradient descent because we are presenting the examples at random, in the random order, and then computing for each example how we need to update the weight. This is not the same as other gradient descent methods, which is really to compute the gradient, then minimize, then compute the gradient again, minimize, and so on. This is stochastic because we are sending the examples at random and making small steps that can change direction at random here. One way of doing stochastic gradient descent is with online learning. Each time we give one example, we update the weights, and then we give another example, update the weights, and so on. Or, if we want to make it faster, we can do batch learning, in which we give a set of examples, compute all the updates for the weight, add up all the updates, and then in the end change the weight of the network. So this may be more efficient in some cases because we are not constantly changing the whole parameters of the network. We're just adding how much we need to update and then doing it in batches. There are some ways you can control the size of the batch. You can do this with the whole training set or with parts of the training set, or this can be optimized depending on the size of the data set that we have. But the idea is that this is a stochastic gradient descent because we are showing the network examples at random and choosing how to go down this surface depending on the example that appears at each time. So let's see how this works for the OR case, trying to divide between these two classes. These are several runs of the neuron, of training the neuron. These are epochs. One epoch is one pass over all the examples, and we need to do many epochs because we are taking a small step at each example. But we see here the quadratic error is reducing, so everything is converging. After 1,000, 2,000 epochs, it's already trained. And we have this separation between the two classes. So for this, it works. However, one neuron cannot classify a non-linearly separable set of points, because in this case, for instance, the exclusive OR function, which is false when both are false and false when both are true, this is not linearly separable, and we cannot fit one line here that separates the two classes. So if we try to train the neuron with this exclusive OR, the error gets stuck here at 0.25, which is the square of 0.5. So this is a quadratic error. 0.5 is the error it's doing because on average it's missing by 0.5 the target value, and so we have this. The error does never reduce, and the classifier cannot really predict it correctly. So how can we solve this problem? We can add another layer. This is a multi-layer perceptron. A multi-layer perceptron is a set of layers of neurons that are fully connected between one layer to the other. So all the neurons on this hidden layer here are connected to the output layer. And if we had more layers, each layer would be fully connected to the next layer. So in this case, we have a very simple network. We have only 3 neurons. One neuron is on the output. It outputs 0 or 1. These two are here on the hidden layer. They also output from 0 to 1 with the logistic curve, but their output will feed into the input of the output layer. And these are the ones that actually receive the values that we want to classify. Also note that we are adding here these bias values, these ones, because this provides an extra weight that serves to adjust where the threshold is, so where the curve starts responding with a 1. So these are the bias weights over here. They are just multiplied by 1, so they can be freely adjusted to set that. Yes, we could just have a 1 here and arrows everywhere. So it doesn't. You can have 1. 1 is 1, so that makes no change. It just would make it would make it harder to copy paste to make the diagram. So basically, that's the difference. So here we have a fully connected feed-forward network. This is a multi-layer perceptron. Feed-forward because all the neurons are feeding forward to the next layer. Fully connected because each layer is fully connected to the next one. We have one hidden layer with these 2 neurons and one output layer with 1 neuron. And we're going to assume all of these have that sigmoidal curve. You can use other functions that are also continuous, and the derivative is continuous, but we are going to use the sigmoidal curve always in this example. So now, we have, to train a multi-layer perceptron, the output layer works similar to what we saw so far. So we need to do this. We go one small step down the gradient of the error, but we need a chain rule to update the weight of the output neuron. The thing is that the output neuron, the weights of the output neuron are not receiving the x values directly. They are receiving the output of the hidden layer. So actually, instead of having an x here at the end, we are going to have the output of the neuron that is on layer n. So this is the neuron on layer n, would be the last layer. Layer m would be the one before, and that's the output that is replacing the x. But other than that, the updates for the weight of the output neuron are the same as if we were using only one neuron. So this is basically the same derivation we saw on the other example. We can, however, usually we call this part here, which is the target value minus the output of this neuron multiplied by the output of this neuron multiplied by 1 minus the output of this neuron. We call all of this a delta that belongs to this neuron, because this depends only on the state of this neuron. So we can compute deltas for each neuron and then simplify the expression and the computation from then on. Because we are going to use the same delta for all the weights on the neuron. So this part is the same for all these weights here. Now, where it gets a bit more complicated is when we go to the hidden layer. So when we are one layer back, we now have to keep on propagating the error backwards through all those different steps. So the output neuron, we went from the error in the output, between the output and the desired value, to the logistic function through the linear combination that gives us the net input until we reach the weight. But now we have to propagate this backwards through all the neurons forward from this neuron on. So if we want to update a weight on this neuron, we need to bring the error at the end all the way back to this neuron from all the neurons that could be ahead. In this case, we have a very simple network. There is only one neuron here, but there could be other neurons in the front layer. So, and we would need to add up all the errors that come from these forward neurons. So that's what we are doing here. This is the propagation of the errors of all the neurons in front. And then we go through the activation of the current neuron, the net sum of the inputs for this neuron, until we reach the weight we want to update. So this is basically the backpropagation algorithm. We keep propagating backwards through the network, adding all of these terms. So to show here more intuitively, suppose that we want to update this weight here. We can measure the error of the output of this neuron relative to what it should be, and the output of this neuron relative to what it should be. We can backpropagate that error from the derivative of the quadratic error by going through the sigmoidal function, the linear combination of the weight of this one, and then we need to go through this sigmoidal function and so on until we get to this weight. But we need to do this part for this neuron and also for this one. And that's what we have here on the sum. This is tracing back from the J1 neuron and from the J2 neuron all the way back to the current neuron that we're in. And then we continue by the derivative of this sigmoidal function and the derivative of the weighted sum of all the inputs. And then we reach the weight we want to update. If this is an input neuron, then we only have the x value that serves as input multiplying by this weight. If there are other layers backwards, then instead of the x is the output of the previous neuron. But the idea is still the same. So if we want to do this more, we have to keep computing these derivatives and going backwards through the network. So this is the backpropagation algorithm. First, we feed the input of one example into the network, and we propagate forward the activation of the network. So we compute for the input neuron the net input for each neuron and the value of the logistic function of the activation of each neuron, and then we use the activation of the neurons of the first layer as input for the neurons on the second layer. We activate those and then go on until we cover all the net. And then at the output we know what the result should have been, so we can compute the error and we can compute these delta values that depend only on the activation of that neuron and what the activation should be based on the labels that we want to predict. And then we backpropagate all these deltas by going through, for each neuron, all the weights that connect to the neurons in front, adding up all those deltas multiplied by the weights, and then propagating through the sigmoidal function of that neuron and the activation, so that we can reach the ones before. So basically we compute the deltas for all the neurons by backpropagating now through the network and computing this from the end to the beginning. Once we have all the deltas computed, we can compute the update for all the weights. And the updates for all the weights will be this small learning rate value multiplied by the delta for that neuron the weight belongs to, and multiplied by the value that is passing through the weight. If it's the input layer, it will be an X value from the features of our example. If it's a layer in the middle of the network, it will be the activation value of the previous neuron. So this is the backpropagation algorithm. Basically, go to follow the multi-layer perceptron forward, activating all the neurons, and then computing all those deltas backwards and update the weights at the end. So let's see how this network here with these three neurons with one hidden layer can solve the exclusive OR problem. We can see that when we make different runs, because we are giving examples at random and we start with random values for the weights, the trajectories are not all the same. At around 20,000 epochs, we have convergence in most of the cases. In some cases, it takes a bit longer. So typically when you're training neural networks, it's useful to try a few times to see how long you need to train them, because it's not always the same how the training goes. This is the result of doing that stochastic gradient descent. It's not exactly the same every time. But we manage at the end to get a good classification of our non-linearly separable problem. So it's telling us that this is the blue class and that one is the red class. And how it is doing this? Each neuron can only separate linearly separable classes. But what happens in the hidden layer, if we plot the output of one neuron versus the output of the other, we see that the neurons in the hidden layer cannot distinguish between the two classes, because this neuron will classify as a low output value both the two blue ones and the red one, and as high output value this other red one, and the other neuron does a similar mistake. It places these three in the low value and that one on the high value. So by itself, neither of those hidden layer neurons can separate the two classes. But when they work together, they have this effect. When we plot their activation values, if we look at both of them together, they are transforming the representation of a XOR function into this representation here that is linearly separable. So the output neuron is actually seeing a different representation of the problem that becomes linearly separable, and it can find the frontier between the two classes. Okay? So this is basically how the multi-layer perceptron is working. The hidden layer is changing the way the data is represented, the shape of the point, so that the output layer can cut where it needs to separate. There are many applications for this. For example, this is a classical example from Mitchell's book, which is an auto-associator. We have 8 inputs here, 8 outputs. We have this layer, hidden layer in between. And we want to train our network so that the outputs are the same as the inputs. And the outputs and the inputs can have 1 and the rest 0. So it can be 1 here and the rest 0, or 1 here and the rest 0, and so on. And in the hidden layer, we only have 3 neurons. And when we train this, after a while, we get this hidden layer representation. So depending on the input, the 8 possible inputs, there will be a different combination of the 3 hidden neurons. One is on the high activation and the other 2 are low. And these combinations are equivalent to the binary representation of the 8 different ones. So we are re-encoding the original point by forcing the network to output the same as the input. Actually, this is now used often in deep learning to re-encode features and to extract that kind of data of information automatically. Not necessarily by using a smaller hidden layer. Sometimes you can use a larger hidden layer, but basically you are trying to re-encode the data in a different representation that is more useful for classification. So in practice, we start with random values for the weights close to 0, because the logistic function saturates away from 0, and we want to be in that region where the derivative is high. Since the initialization of the weights and the examples are presented at random, we should run several times to see how things usually go, because not all runs will be exactly the same. So we start with this, with the inputs. We should standardize or normalize them. It's not good for a neural network to have input values that are very high or very low. It makes it harder to train, especially because we use a learning rate that is the same for all dimensions, and when we multiply that by the input value, if the input values are very large in some cases, it will move faster than in the others. So you should normalize of standard size here. The logistic function outputs between 0 and 1, so this should be our class label, 0 or 1. And if we have multiple classes, we can use several output neurons. So we're going to see a bit more about that later on in the course. We use this stochastic gradient descent, meaning that we are presenting examples at random and then choosing for each one, computing what is the update that we want to do. We can do the updates in batch or online, one by one. One pass through all the examples is one epoch. So we don't usually do this by sampling the examples. We just take all the examples, order them at random, and make one pass. And then order them at random again and make another pass. So that at each epoch, one example is presented one time. Each example is presented one time. It's just the ordering that changes. And then we evaluate the error, the quadratic error, for training, for cross-validation, whatever. Now, we can also do regularization with neural networks. I'm just going to give two examples. One simple example is to do early stop. This is the validation, cross-validation error in blue and the training error in red. As we keep training the network, the training error continues to decrease. But depending on the fault, the cross-validation error can start increasing. So on average, the cross-validation error starts increasing at about 40 epochs or so. So we should stop training here to avoid overfitting. This is one way of doing regularization with neural networks. Another way is to force useless weight to go down to 0. So we can, when we do the update rule, when we update the weight, we can also subtract a tiny fraction of the weight value, so that it will tend to go towards 0 if it's not important for classification. So if it tends to be increased to decrease the error, it will be large. But if it's not working, if it's not doing anything important, it will tend towards 0. So these are two examples of how we can do regularization in neural networks. So basically we saw the classic idea of the perceptron, the nonlinear response to a linear input, a linear combination of the inputs, and we saw this stochastic gradient descent. So actually, so far, the training of the models, such as with logistic regression, when we want to find the parameters, we were giving it to a black box of some optimization algorithm and then get the parameters. Here we saw exactly how the algorithm works by presenting each example and going down a small step in the gradient of the error. We saw how several layers can help solve the problem of nonlinear separability by re-encoding the shape of the data in the hidden layers. And we saw backpropagation and regularization. You can read several on all these books about multilayer perceptron and machine learning. Mitchell's book is a bit old, but the backpropagation algorithm is very detailed there and very well explained. One thing to note, and sometimes it happens, that sometimes the output neuron of a neural network is not sigmoidal but linear, because maybe we want a linear output. And that changes the equations a bit. So pay attention that in the example in Alpaiden's book has a linear output, and the derivatives are different for the backpropagation. Okay? And that's all for today. If you have any questions.